Hello, thanks for stopping by. My name is Marcel Hussing, and I'm a computer science PhD student at the University of Pennsylvania. And I have a question for you. Do you think reinforcement learning agents have the ability to decompose the tasks they are learning? Well, this is exactly the question my co-authors Jorge Mendez, Meghna Gummadi, Eric Eaton, and I asked ourselves. But how would we test it? We came up with an idea. What if we build a benchmark that exhibits compositional structure by design? If an agent would do well on such a benchmark, we would have evidence that it can in fact make use of composition. Building this benchmark is what we did in our current work, which is called CompoSuite, a compositional reinforcement learning benchmark. Our work consists of three major contributions. First, we provide 256 compositional simulated robotics tasks with distinct optimal policies. Second, we have schemes and metrics that allow for reproducible evaluation of future approaches. And finally, we provide an experimental evaluation on single task, end-to-end multitask, and modular multitask reinforcement learning agents that show the shortcomings of current approaches when it comes to modular decomposition. Now, let's take a step back. One of the biggest problems with current reinforcement learning approaches is that they are very data hungry. So suppose you wanted to learn all of our 256 tasks, and each task would take 10 million time steps to learn. We would need 2.56 billion time steps to be able to learn all our tasks. Now, there are many directions of research trying to improve the data efficiency of RL agents, and one of these directions is called functional composition. So what exactly is functional composition? Suppose you're teaching your robot how to sweep the floor and how to take out the trash. Each of these tasks consists of several components like picking up a broom or dropping a trash bag. The robot should be able to decompose these tasks into subcomponents. So then in the future, when we want to teach our robot a new task like cleaning plates, it already knows, for instance, how to pick up an object from previous experience. How do we build this idea into a benchmark? Let's talk more about CompoSuite. CompoSuite uses a Bujoko simulator and is built on top of RoboSuite, a robotic simulation framework that allows for easy extension of new tasks. We designed our tasks to consist of 4 axes, each of which has 4 different elements to choose from. More specifically, in every task, the agent controls a robot arm, needs to manipulate an object, achieve an objective, all while trying to avoid an obstacle. So here are some of the tasks. Suppose our robot arm needed to pick and place a box. We could then switch out the robot arm and go from an EVO arm to a JACO arm. Next, what if we change the objective and now the robot arm needs to push the object instead of picking and placing it? Then we substitute the box by a plate to change up the object. And finally, we put an obstacle in the way of the agent so that it has to circumvent it. By combinatorial explosion, we create our 256 tasks. Before we look at experimental results, here are some technical details about CompoSuite. In the box above, you can see the different elements to pick from. For instance, the objects that we choose all require different grasping strategies, leading to different optimal behavior. While the plate can only be picked up from the side, the box can only be picked up from the top. On a technical side, we have standardized the observation space, which contains proprioceptive information, object, goal, and obstacle positions, as well as a multi-task descriptor. The action space consists of 1 action per joint and a grasp action, and all chosen robots are 7 DOF arms. Lastly, we provide shaped reward functions for every objective to facilitate quicker learning. Now that we've understood what CompoSuite is about, I'm handing it over to Jorge, who will show you some of the results on our benchmark.
So how do existing approaches fare on CompoSuite? Our evaluation seeks to show that CompoSuite is not too complex to start making progress. The CompoSuite tasks are indeed compositionally related, and there is substantial room for improvement for future work. In each experiment, we trained the agent on a sample of training tasks, which we used to assess the agent's speed of learning, and then evaluated its zero-shot performance on a sample of test tasks, which we used to measure the agent's ability to compositionally generalize. In one experiment, we sample 56 tasks and train a separate PPO agent on each task. After training for 10 million steps, the agent solves only around 40% of the tasks. Then we train a typical multitask agent, with all tasks using a single shared policy network. Intuitively, if this agent discovers the relations between tasks, it should learn faster than the single task agent. But unfortunately, that isn't the case. It just learns at about the same speed. So next, we bake in the compositional structure directly into the network by using modular nets, with each module corresponding to one of the task components. But once again, this agent doesn't really achieve any substantial speedup. So, are things hopeless? Is CompoSuite just not compositional, or is it too hard for current RL methods? Another hypothesis is that we're just not using enough tasks, and the agent requires seeing a lot of task combinations in order to find the relations across them. So we repeat the experiment, but now using a sample of 224 training tasks. The single task agent again achieves around 40% success. The multitask agent doesn't really improve upon that, but then the modular agent is able to solve almost all the tasks. And if we now look at performance on the unseen tasks, we find that when trained on the larger training set, the modular agent is able to solve almost all these tasks without having ever trained on them. We show in the paper that this is not due to tasks being very similar, since it is nearly impossible to solve one task by using the policy for another task. We do definitely encourage you to look at the remaining experiments in the paper, which show smaller variants of the benchmark, zero-shot tests after seeing a component only once, and more results. Our paper demonstrates that there is substantial room for improvement in current RL approaches. As shown in our results, RL doesn't really generalize compositionally unless it trains on almost all possible combinations. We need to develop techniques that learn generalizable components after seeing them in far fewer combinations. Taking this to the extreme, one additional setting in our paper requires the agent to, for example, generalize to all pick-and-place tasks after training a single pick-and-place task. The modular architecture we used is given ground truth knowledge about the components of each task and how to combine them. How can our agents discover these structures autonomously? These and more questions can be studied via experimentation on CompoSuite. Thank you for watching, and please check out CompoSuite and reach out if you have any questions or suggestions.